Hi everybody. I guess at this point you might have completed most of the functionality of the file syscall. So today we're going to cover some minor issues in file syscall. For example, how to initialize a console and where to initialize them, and the UIO usage, and one of the file syscall dupe 2. Today we're going to mostly focus on the process syscalls, fork, exec, the most difficult tools, and the pair of syscall called exit and WPID. So hopefully, at the end of the day, you may get an idea how to implement fork and exec, especially the exec argument passing stuff. And at the end, I will briefly cover some bullets that you should cover in your design document, which students mostly forgot about them. So at this point, you should be able to pass this file-only test, right? It's the most basic or most basic test program that tests the file syscalls like open, read, write, close, lseek. It won't touch any process syscalls, so you should be able to run it before you run any process syscalls. So I guess most of you or all of you guys here have passed this test. Yes? Yeah? Great. And so there is another test program called bad-call. Basically, it will pass in all kinds of bad arguments to test your argument checking. So you probably wanted to test this so after you enter this in the OS 161 menu, P test being bad-call, you will see a bunch of options. Basically, you can choose which function to test. In terms of file syscall, you want to test this to make sure that you defend against all possible bad arguments. So one common miss of the file syscall is how to initialize the consoles. We all know that in a process's file table, the first 3 entries are special. They are 0 for std in, 1 for std out, and 2 for std error. And in OS 161, all the consoles are just files. So that means you can open them just as you open other files. So you can open the console files using this function call called VFS open. Basically, you need to supply the name. So console has a special name called con column, and the flag depends on what kind of console, what kind of standard in or standard output you are opening. You may want to pass different flags for them, either read-only for std in or write-only for std out and std error. And for the mode, you want to pass this. So this is how you open the console. After this function call, you get a vnode representing the console files, which you can do read or write on that. So one thing to note here, I saw students asking this over and over again, that they ask this. So I open the console correctly, std in open correctly, but the second time I call VFS open, the VFS open fails for some reason they don't know. The reason here is that so the first argument to VFS open is actually the file name, right? And inside the VFS open, there is some function or some code that actually alter the content of the file name. So after VFS open returns, the file name is no longer con column. So if you call VFS open using that file name again, you won't be able to open the file properly. So the thing here, is to every time you call VFS open, before that, you want to make a separate copy of the file name, which you don't care about. And you call the VFS open using that file name. And the next time you call VFS open using this file name, you again make a copy of that file name. So this time you make sure, in this way you make sure that every time you call VFS open, you actually open this file instead of some other file names. And so Now you know how to actually open the console files. The next problem is to when to open them, right? I guess some students get the idea to, actually I did this 2 years ago, that I do not open the consoles until the user actually read or write on them. So it will work. Basically, it works as follows. So every time in sysread or syswrite, you check if the first three file handles are null. If they are null, that means I have never opened the console for them. And for this process, I call webfs open on it. So it will work and it will pass the test program. But this is not the correct way to do it. So basically, imagine this case. So what if the parent close one of the std in, std out, or std error before calling the fork, before create a new process? By the semantic of the file of fork is that the child should have the identical or exactly the same file table as the parent, right? It means that ideally the child's file table, the entry for example, std out should be null. That is on purpose. The parent closed that file. But if you do this lazy initialization and in syswrite you detect that std out is null, you are not supposed to open it for it, because at that time that file has already been closed. If the child wants to write to that file, it has to open it again. You should not open it for the child. So why we need to open the consoles for the for a process to write or read from it? That's because in kernel space we don't need to open it, right? We just directly call kprintf or kgets to read or write from the console, right? It's only the user space thread that need the so the kernel doesn't need to do VFS open on the console files to read or write it. Only the user space thread need. And where the first user thread is created. So when you boot up your kernel and enter the menu, are you in user space or kernel space? Kernel space, right? Because that menu is a kernel space thread. So when is the first user thread is created? For example, shell. You want to run shell. You type the command either p/bin/sh or just s. That's where the first user thread is created, right? And only that thread needs the console files. And all the user threads thereafter must be forked by the first user thread, right? So the right way to do it is you open the console files just for the first user thread. And all the following user threads just inherit the console files from the first user thread. That way you don't open the console multiple times and you just increase the reference count of the file handle for the console, right? Yeah, the first user thread is created in manual when you type some command. So, and that's probably where you want to initialize the console. More specifically, the function is first, when you type the command S, the manual will call thread fork to create a new thread, right? And then in that new thread, there is a function called run program, which basically replaces the current address space with a new user address space and execute the user thread. So in that function, you want to set up the console files std in out error for the first user thread, and then just leave it alone. So in sysread and syswrite, you don't have any special cases to check if the FD is 012 and if the corresponding file handle is null. You can just treat them all universally, all as the normal files, right? Where are you guys initialize consoles? Where did you open the console files? Load what? Load elf. You do inside load elf or in run program? Outside load elf. Yeah, that's the correct place to do it. Yeah. So right now the test program cannot tell where you initialize the console, as long as you really initialize for the user thread. But in the future, Jeff may come out with some new test suite that actually test where you initialize them. So it's better to do it in the right way at the first place. Yeah.
So we are not supposed to do lazy initialization, but is there anything wrong with doing it?
This way, lazy initialization? Yes, I'll just talk about it. So suppose, yeah.
Yes, I will be opening the console files again and again.
Again. Yes.
But that's the only problem, right?
Not the only problem. Not the only problem. That's the key problem here. So suppose the parent close std out before call fork, and then parent call fork. So when parent close std out, the file type entry in the parent for std out is null, right? And then in fork, because you are copying the file table, the child file table entry for std out is also null. At this point, you don't know if it's null because you never opened it for the child, or it's closed on purpose by the parent, right?
So when the child writes on console again, so he would get a new file handed.
No, because so right after fork in the child thread, the std out is actually not available, right? So at this point, if the child wants to print out some stuff, it is supposed to get some error because he wants to write some file that doesn't exist.
That's what we do with lazy initialization, right? If that particular file is not open.
No, that's the expected behavior of the child. The child should not be able to write to the std out at this point. That's why the parent closes std out. Right? If you do lazy initialization, you actually enable the child to write to std out. That's not correct, right? The child is supposed to fail if the child wants to write to std out, right? So the second issue of the file syscall is the UIO structure. Basically, UIO is a mechanism to describe what kind of I/O you want to do. Either you want to read from disk to user space or to kernel space, or you want to write some content from user space or kernel space to disk. So basically, there is this function that provides a convenient way to initialize the UIO structure for kernel space I/O. By kernel space I/O, I mean from kernel space buffer in memory to disk, or from disk to kernel space buffer. So here we take the I/O vector and UIO structure as argument. We pass in where the buffer is, how much buffer do you have, and on which position we want to read or write from the file, and what kind of operation we want to perform, read or write. So here we first initialize the I/O vector variable. We set the kernel base and the length of the buffer, and we point the UIO I/O vector inside of the UIO structure to this I/O vector, and we only have one I/O vector so the IOV count is 1, offset is position. This resid, it means that how many bytes left of the UIO. So initially, before we perform the UIO, this should be the length of the buffer, meaning that we have not write or read any bytes. So the remain bytes is the length of the buffer. And the second flag for the UIO is because we are doing kernel I/O, is this sys space for kernel space. And if you go to the definition of this, you will see two other segment flags, which is UIO user D space and user I space. Basically, D space for the data, I space for the code. And the operation, read or write, UIO space. Because we are in kernel, we don't actually need a address space, so we just set it to null. So after this function, now you can use the UIO to, for example, in load elf, you will probably see this function that read the content sorry, not in loud elf. This function can be used for the kernel to read or write files. So I saw a lot of people doing this in their read or write. So in read or write, user give you a buffer, which is in user space. For example, in read, I saw people doing this. So they first use UIO kinit to initialize the UIO structure for kernel space I/O, because UIO kinit is already there. It's very easy to use. So they allocate a chunk of kernel buffer using kmalloc and initialize the UIO for this kernel buffer, and then use VOP read to read the content from disk to the kernel buffer. And then they use copy out to copy the content from kernel buffer to user buffer. Right? This is basically the data flow. They never exchange data between the user buffer directly to disk. They always use a kernel buffer to do the I/O. And that's not the right way to do it, right? So suppose the user wants to write 1 megabyte of data. It's dumb for you to allocate another 1 megabyte of buffer in kernel space, because user has already allocated the buffer in the user space, right? So it's dumb for you to just copy the data from user space to kernel space, and from kernel space to disk. It will be a waste. Both in time, you are doing the copy twice, and in space, you are allocating the buffer twice. So the right way to do it is you can set up the UIO to do directly between the user buffer and disk. So you don't have to allocate the kernel buffer at all. And as the name indicated, this UIO initialization function is just for kernel space I/O. So according to this function, actually you can come up with your own version of the UIO initialization function called UIO uinit for user space I/O. So to do that, you just need to make these changes to that function. First of all, now because you are doing user space I/O, you want to set up the IOV U base instead of IOV K base. And then secondly, the segment flag should be the one of the UIO user D space or user I space. Normally it will be user D space because you are copying the data. And the UIO space, which is the address space, you need to set it to the current thread address space. And after you make these 3 changes, you can conveniently change the UIO kinit function to UIO uinit function, and then directly do the UIO between the user space and the disk. You don't have to do extra copying or extra buffer anymore. And also, as I just mentioned, this variable in UIO told you how many bytes left after the UIO. So to compute how many bytes are actually being read or write, read to the disk, read from disk or write to the disk, you just need to use the initial length of the how many data you have minus this variable after the VOP read or VOP write, and you will get the actual bytes that actually write or read from the disk. Any questions on this? How many of you use the actual kernel buffer to do the I/O in sysread and syswrite? You do? You may want to change that. It's not efficient. It's okay at this point because you have plenty of memory, right? In assignment 3, actually you will have a very tiny of memory, and you will do swapping, and you will do a lot of I/O in that case. And in that situation, if you allocate a bunch of kernel buffer, you will run out of memory more quickly than others, and you will do more swapping.
But if I do it directly from user buffer to disk, isn't there a chance of the data being corrupted or something?
Yes, that's the great thing about UIO. Actually, if you do VOP read return the success or not, right? VOP read or VOP write will actually check if the user space buffer is correct. If the user space buffer is not correct, it will return some error instead of performing the I/O. You don't need to do copy check. VOP read or VOP write will do the copy check for you. So you just pass all the information, packed all the information to the UIO structure, and pass this URL structure to VP read or VP write, and all the checking stuff will be done there.
I don't need to do copy in and copy out.
No, you don't need to. Yeah, the code will be much simpler if you do this way. Yeah. So the final point about this file syscall is dupe2. At first glance, dupe2 is kind of easy to implement, right? It's within 10 lines of code, I think. But the difficult part is probably to understand how dupe2 is supposed to use, right? So suppose we all know, I guess you all know that in Linux there is a command called echo. You can provide a string to the echo command, and we just print out the string to the stdout, right? And this is the minimal example or implementation of echo.c. We do nothing in the main function. We just have one meaningful sentence called printf whatever the argument is, and we return 0, right? And this is the minimal shell.c. So when you type echo, the shell will know that you want to run this program, and shell will call fork to create a new thread and call exec on this binary, and it may also pass the actual arguments, which I didn't write it down here. So this all looks good. Now suppose we know that shell supposes IO redirection, right? That means instead of printing the content to the console, I want to print the content to some file. So there is a special symbol here, meaning that redirect the output to this file instead of print it, right? Now, the question is, do we need to modify the echo.c so that the echo.c understand, oh, now the user don't want to print it to stdout, I should write the content to the file, right? Do we need to modify the echo.c to enable the IO redirection, right? That's what dupe2 does, right? We can implement this functionality as this. So we leave the echo.c as it is. We don't change it. So in echo.c, we still do printf whatever the argument is, but before calling fork, we call this. So the shell now understand that we need to do IO redirection. So the shell open the output file and call dupe2. So the first argument is the new file descriptor of that output file, and the second argument is stdout file number, which is 1, right? After this syscall, what happened? So in the file table of the shell, the entry for stdout and the entry for this file is actually points to the same file handle, right? There is no more stdout. Stdout and this fd points to the same file handle. Now we can actually close the out. Why can we do that? This won't close the actual file, because now there is two file descriptors point to the same file handle, so the reference count of the file handle is 2 instead of 1, right? If it's okay, we close it. We just decrement the reference count by 1 instead of actually close the file. Now we do the fork and exec part. So in echo.c, we still do printout. We still do printf. Printf will write the content to stdout. But in that case, the stdout is actually points to this file instead of the console. So without modifying the code for echo.c, we implement the IO redirection. That's how dupe2 can help to modify the file table. Actually, dupe2 is one of the few functions that can change the file table. So open can change the file table. You may need to allocate a new FD. Close can change it. And then dupe2. Read and write doesn't change the structure of the file table. It just modifies the offset of the file, right? So open, close, and dupe2 change potentially the structure of the file table. Any questions on this example? Okay. So inside div2, as I mentioned, the div2 implementation is quite easy. You basically need to do two things. One is close the new FD if it's already opened. In the previous case, we first close as standard output for the current thread, and then we point new FD to old FD. So now new FD and old FD points to the same file handle. And as the menu says, this is different from open the file twice. If you open the file twice, you will get two file handles with separate offset. Right? But if you call div2, actually there will be only one file handle pointed by two file descriptors. Okay, before we go on to the process syscalls, do you have any questions about the file syscall in general? No? Good, okay. So for the process syscalls, similar to the file table, you may want to maintain a system-wide process table. And each entry of the process table represents a process. So inside that process structure, you may want to record what's the process ID, and potentially what's the parent process ID of the current process. Has this process has exited, and what if it's exited, what's the exit code? And also, how this is about the coordination between the parent and child thread in exit and web PID. You can put all this information to the structure thread. It's okay, because in OS 161, the thread is just a process. So you can put all this information here. But later on, I will point out why you want to create a new structure called process instead of put all the information in the thread structure. In terms of fork, basically what it does is it clones almost everything of the current process, and so it first creates a new process and copy the current process, all the content of the current process to the new process. And so I highlight the almost exactly here. Exactly means the fork copy almost everything to the new thread. But there are two things different. One is the process ID. It's kind of trivial because every time you create a new process, you want to allocate a new process ID for the process. Of course, the process ID is different. Another different thing is that the return value of the fork. So as in the previous example, if the fork returns 0, meaning we are the child thread, or we are the child process. If it's non-zero, some positive integer, we know it's a child process PID. All right. So let's first focus on the exactly part. How do we copy exactly the current process? To answer that question, you may want to think about this question. So what's inside the process? We first need to figure out what's already there. Then we can copy them, right? So what's inside the process? We have a file table. That's one thing, and process ID. No, we don't want to copy the process ID. We want to allocate a new process ID for the new child thread. What? Trap frame? Yeah, that's one thing. Trap frame is not a part of the process. Trap frame only exists when you are trapping the kernel, right? Register. That's basically the context of the execution, right? The trap frame contains all the registers at that point of the parent process. So we have a file table, we have a trap frame, and what else? Address space, right? Address space is basically everything in the memory. We want to copy everything in the memory or belong to the parent thread to the child thread. So the child is almost identical to the parent thread. So we have address space, basically contains all the code, data, and stack. We have file table, we have a context. Context is basically the state of the execution. In this scenario, it's a trap frame. So how to copy them? Well, we have one function called thread fork, which will basically copy almost everything inside a thread so it first create a new thread and copy almost everything to the new thread. And we need to do a few extras copy here. First, we need to copy the address space. because thread fork doesn't do that. And then we need to copy the file table, right? When you copy the file table, basically means it's just about reference count maintains. But now, so previously you have one file table entry points to one file handle. Now you have two file table entries point to the same file handle. You want to increase the reference count of the file table entries. And you also need to copy the parent's trap frame. This part is not as easy as it seems. So first of all, every time you trap into kernel, you have a trap frame. So you first you need to pass that trap frame into your sys fork. And then you need to allocate some buffer to contain that trap frame, because the trap frame is allocated in the stack. When the parent fork returns, the content in the stack disappears. So you want to make a copy of the trap frame. And then somehow you need to pass the content or the buffer that contains the trap frame to the child, so the child can set up its own trap frame. So the trap frame is actually related to the almost part. Now we already copy almost everything to the child, and so when you call thread fork, you actually need to pass the entry point to the new thread, right? That will be the first function executed by the child thread. And in that first function, you want to make a few changes to the new child thread. So first of all, you need to, for example, set up the trap frame. And then, the first thing you want to do is modify the trap frame, because you want the child to return 0 instead of the PID, right? So you need to modify a particular register in the trap frame to make the child feels like the fork returns 0. And also you need to forward the EPC by 4, so the child won't repeat call the fork syscall. There is one function called enter forked process. As the name indicates, it's supposed to be the first function of the child. Just that the prototype of this function is not that correct. So the thread fork actually expects entry point that accept 2 arguments, right? One is void star, another maybe unsigned long. And this function only accepts 1. So you want to modify this function so that it takes 2 arguments. And inside this function, you may want to do a couple of stuff that set up the child thread property. The first is that you want to activate the address space, basically call this function. So the parent has already copied the address space to the child. And at this point, you want to activate it. So actually, at this point, this function does nothing, because we are still using the dump VM. We don't need to activate address space before using it. But it's important we make this call anyway, because in assignment 3, you will actually need to modify this function to actually activate the current address space. So it's a better idea to just call it to make it right at the first place. And you want, as I just said, you want to modify the trap frame to make the child feels like the fork returns 0 instead of the PID. And also, at the end of this function, you are supposed to call one function called MIPS user mode. And you will pass the trap frame to the MIPS user mode. Actually, that function expects the trap frame in a particular place instead of the heap. So the parent copy the trap frame to kernel's heap. By heap, I mean the memory allocated by kmalloc, right? And then you cannot directly pass that trap frame to MIPS user mode. Because in MIPS user mode, we'll check if the trap frame is in kernel stack. So what you want to do is copy the trap frame from kernel heap to the current user thread's stack. You really understand what I'm saying? Actually, this is kind of tricky here. It sounds like very tricky, but in reality, it's very simple. So what do you have done to the trap frame? So in sysfork, in parent sysfork, you get a trap frame. And you do kmalloc of the trap frame to make a copy of the child frame, and you pass that pointer to child thread. And then the child are supposed to use this child frame, right? But when you call MIPS user mode, it's better to show some code about this. So here. So this is the function that enter user mode, and it takes one argument called the child frame pointer, right? And go down here, it actually checks if the child frame is in current thread's kernel stack. If you directly pass the child frame that's in the kernel, the parent passed in, it will fail this k assert, and it will get some panic stuff. So you need to copy the child frame to current thread's kernel stack before you call this function. Have you already done this before? Or have you already completed this part at the end of fork? You have done that? You are doing it? It's not working? Why? Yeah. Does it panic?
Is there any other command that you need to run before fork?
No, you can just so here is how to test the fork test. So first of all, we have a test program called test bin fork test, right? So if what?
That is the program I'm running.
That's
the program I'm running.
Yeah. Did you pass this?
Yes.
You passed it.
No, I did not pass it.
Yeah. So in kernel manual, you can do p test bin fork test to test a fork. So ideally, if everything is all right, it will print 2 zeros, 4 ones, 8 twos, and 16 threes. And there should be no panic. You probably need to complete the wet PID and exit to run this test. Yeah, because otherwise, because as this test, there are multiple user threads. They need to coordinate. So you need to implement the wet PID and exit before you can run this test. And also there is a test called fork bomb. Basically, what it does is just keep call the fork syscall until there's no more memory. So ideally, if everything is correct, you shouldn't have any panic or errors. The only error you get are this. The only error you are allowed to get is this. So the Camelot cannot allocate new memories, because that means you run out of memory. The exact part is even trickier in terms of the argument passing stuff. So there is already one function called run program that does most of the job of the exec. It will load elf to the memory and set up the address space and wrap it into user mode. So what do you need to do besides what's already there in run program is the argument passing. Basically, when user call exec, user pass in a pointer to the arguments. You need to copy all the first. You need to make sure all the arguments are correct by copying them to kernel space, and then before you enter the new user space, you need to copy the arguments out or back to the new user space. So the two copies here are the difficult part of this exact Syscall. And so, for example, if you run this in the OS 161 shell, you run test bin argtest, so you provide 3 arguments for OS 161 and exec. What's inside the user space is like this. So user pass in a UX array to you in exec syscall. It's basically an array of character pointers. The first element points to the first argument, and the second element points to the second argument, and so on. So the first thing you need to do upon entering the exec is to make sure you can copy all these arguments into kernel space correctly without any error. If you encounter any error in the process, you can just fail or return some error code. The thing to note here is that you actually need to, so these are the three actual arguments. This array is just a way to organize the arguments, right? You actually need to copy these arrays into kernel memory because these arrays itself may be illegal or some malformed user's address. So you first need to copy the pointers one by one into kernel, and then you can copy the actual content of the arguments. So at the end of this first stage, you should have all the arguments in kernel space. You can organize it any way you like, but that's just one way to organize them. So you also have a pointer array, and each of them points to arguments. Have you go to the exact part, reach the point? No? You're still working on the fork? Yeah. Exact should take twice the time as fork, I think, in my experience. So after you have already copied all the arguments to the kernel space, now you can just totally forget about them. So now you know all the arguments are correct. Then, so you do all the stuff like load elf and as create and all that. So before you call the enter user mode or enter user process, you need to copy the arguments from kernel space out to the user space. So here we already have the kernel arguments organized as follows. Eventually, just before you call enter user mode or enter user process, the arguments of the user space, this is just one example of what it looks like. So you have you have an array of pointers, and each of the pointers points to one of the arguments. This is just one example of the final layout. You can lay out basically no matter how you want. So you can put the arrays at the top of the user stack. It doesn't matter because the enter user process takes two arguments, right? At least two arguments. One of them is a UX, basically this is the start address of the pointer array, and another is stack PTR. So when you create address space, the stack pointer is at the very top of the user space, which is 0x milli in this OS 161. And so you need to figure out how many space you need, right? That space includes all the actual content of the argument and also the pointer array. As soon as you figure that out, you can just minus the stack pointer by that length to reserve space for the arguments. And then now you have all this space. You need to pack all these arguments into this space this way. So the minimum requirement is that you have an array of pointers. This has to be consecutive, and you have to pass the start address of this. The orders of these arguments doesn't matter. As long as you point to them, user can always access them using this pointer array, right? And in the process, you may also want to do the padding stuff, because in the MIPS can only access the pointers that are aligned by 4 or 8. So in this case, for example, the space occupied by full is actually 4 instead of 3, because FOO plus 10 to terminate the string. So it's already aligned. What about this string? So 1, 2, 3, 4, 5. We have 5 characters, and the actual space occupied by a string is actually 6 plus 10, right? 6 is not aligned by 4. So you may want to pad 2 more zeros at the end of this string to make the length of the string to be 8, for example, so that when you access it, you don't get some address violation or something like that. Any questions about this figure? So how to copy the arguments from user space to kernel, and how to pack all these arguments properly to user space so user can access them. Okay. Finally, the exit and WebPRD. This is a pair of functions. You may want to design them all together because it's all about the coordination between the parent and child process. So in exit, you first need to store the exit code somewhere, and then indicate that this process has exited and call thread exit. So after you call this function, the thread will be added to the zombie queue of the system, and this function will periodically call thread destroy on the zombies. So this is probably why you want a separate process structure instead of put everything in the thread structure, because it's possible that thread structure is destroyed before the parent can call WebPRD on it. So the parent needs to first check if I can wait on this PRD, wait for child exiting, and collect the exit code and destroy the child, parent structure. You need to figure out a way to coordinate between the parent and the child. So you also need to modify the kill current thread to, instead of panic, you actually kill the current thread. And this is one minor issue about the shell. I will cover this once you got that point. So this is 3 most bullets that are missed by students who submitted the design documents. You may want to cover everything so you can get points for the design document stuff. Okay? Okay, that's it for today. Thanks.